Hello friends, welcome to the channel Physics by IITians.
Hello friends, in this video we shall revise some important formulas from the topic electrostatics and magnetostatics. So let's start. The electrostatics, you should know about the electrostatic potential E equals to minus grad phi, where E is the electric field and phi is the electrostatic potential. There are potential difference between 2 points, that is phi A minus phi B can be written as integration over A to B E dot dl, where phi A is the potential at point A, phi B is the potential at point B, or it can be written as minus of integration over B to A E dot dl. Poisson equation del square phi equals to minus rho by epsilon naught, where rho is the charge density and epsilon naught is the permittivity of the free space. A point charge which is located at r prime, and we want to find out the potential and electric field at another point r, then phi at r is q by 4 pi epsilon naught mod of r minus r prime, and E at r is q into r minus r prime divided by 4 pi epsilon naught into mod of r minus r prime whole cube. Field for a continuous charge distribution in free space is E at r equals to 1 by 4 pi epsilon naught integration of volume rho r prime minus r prime divided by mod of r minus r prime whole cube d tau prime. So it is for the volume configuration. If you want to know this, if you are given the surface charge density, then it will be sigma ds or sigma ds prime. For the line charge density, it will be lambda dl prime. Okay, so d tau prime here the volume element, and r prime is the position vector of the d tau prime volume element. Magnetostatics, the magnetic scalar potential is phi m, then the magnetic flux density B can be written as B equals to minus mu naught into grad phi m. Phi m in terms of the solid angle of a generating current loop is phi m equals to I into omega by 4 pi, where omega is the loop of the solid angle. Okay, so Biot-Savart law can be written as B at r is mu naught I by 4 pi integration of dl cross r minus r prime by mod of r minus r prime, where r prime is the position vector of this dl element or dl current element. Ampere's law is curl of B equals to mu naught J. This is Ampere's law in the differential form, and J is the current density. Ampere's law in the integral form is closed integral over B dot dl equals to mu naught into I total, where I total is the total current through the loop. Capacitance for the sphere of radius A, C equals to 4 pi epsilon naught epsilon r A. For the circular disk of radius A, C equals to 8 epsilon naught epsilon r A. For the two spheres of radii A, they are in contact. Capacitance C equals to 8 pi epsilon naught epsilon r A ln 2. For the cube of side A, C is nearly equals to 7.283 into 10 to the power minus 11 epsilon r A. There are two concentric spheres, one with radii A and another with radius B, where A is less than B, then capacitance C equals to 4 pi epsilon naught epsilon r AB divided by B minus A. For the coaxial cylinders of radii A and B, where A is less than B, capacitance C equals to 2 pi epsilon naught epsilon r by ln B by A per unit length. And you should also know the series combination of capacitance and parallel combination of capacitance. Parallel combinations, capacitance will be added simply like C1 plus C2 plus C3, and for the series combination, the inverse reciprocal of the capacitance will be added, that is 1 by C equals to 1 by C1 plus 1 by C2, like this. So inductance formulas are for the n-turn solenoid, they can be straight or they can be toroidal with length L, and area A is L equals to mu naught n square A by L. For coaxial cylindrical tubes, radii A and B is L equals to mu naught by 2 pi ln B by A, where A is less than B, and this is inductance per unit length. For the parallel wires of radii A and separation 2D, L is nearly equals to mu naught by pi ln 2D by A per unit length for 2D greater than A. For the wire of loop A, radius A bent in a loop of radius B, which is greater than A, then L equals to mu naught B into ln 8B by A minus 2. Okay, so electric fields, suppose there are charge sphere of radius A and charge Q, then electric field is q by 4 pi epsilon naught a cube into r vector where r is less than a, or q by 4 pi epsilon naught r cube into r vector where r is greater than equals to a. And this is for uniformly charged sphere. For uniformly charged disk of radius a and charge q on the axis z, E at z is E at any point on the axis, that is E of z, is q by 2 pi epsilon naught a square into z, 1 by mod z minus 1 by root over z square plus a square. For the line charge where charge density is lambda per unit length, E at r is lambda by 2 pi epsilon naught r square into r vector. The electric dipole moment, where we are defining dipole moment as P, then ER, that is the electric vector field intensity, is ER equal, the R component is P cos theta by 2 pi epsilon naught r cube. The theta component E theta is P sin theta by 4 pi epsilon naught r cube, where this spherical polar coordinates we have written in terms of r and theta is the angle between the dipole moment P and the position vector r. Charge, for the charge sheet, the surface charge density is sigma, then E is sigma by 2 epsilon naught. Magnetic fields, suppose we have a uniform infinite solenoid passing current I and in turns per unit length, then B equals to mu naught Ni for the inside, that is axial magnetic field, and it is 0 outside the solenoid. Uniform cylinder of current I and radius A, B at r is mu naught I r by 2 pi a square for r less than a, and mu naught I by 2 pi r for r greater than equals to a. Magnetic dipole moment, we are defining it as m, and theta is the angle between the magnetic dipole moment and the position vector r. Then r component of magnetic field due to this dipole Br is mu naught m cos theta by 2 pi r cube, and theta component d theta is mu naught m sin theta by 4 pi r cube. For the circular current loop of capital N turns radius a and along the axis, that is z, we take Bz equals to mu naught Ni by 2 a square by a square plus z square whole to the power 3 by 2. For the suppose the axis z of a straight solenoid n turns per unit length current I, then B axis is mu naught Ni by 2 cos alpha 1 minus cos alpha 2. This is the straight line, and this is the angle is alpha 1, and this angle is alpha 2. Okay, and this is at any axial point along the z direction. So for the image charges, the real charge is plus q at a distance, suppose it is of b at a distance b from a conducting plane, then the image charge at a distance will be minus b and the amount of image charge will be minus q. Suppose the real charge plus q at a distance b from a conducting sphere of radius a, the image point will be a square by b and the image charge is minus qa by b. Suppose the point charge, real charge plus q, is at a distance b from a plane dielectric boundary and it is seen from the free space, the image point will be at a distance minus b and the image charge amount will be minus q into epsilon r minus 1 by epsilon r plus 1, and if it is seen from a dielectric, the image point will be plus b and the image charge amount will be plus 2q by epsilon r plus 1. So thank you friends, thank you for your watching this video. I hope you like this video. It will be very helpful for your exam. So all the best for your cooperation, and like this video, share with your friends. Thank you.